As was just said, thank you very much. My name is Oskar Laverny. This is RIM Alhajal, and we are here to discuss an implementation that we did of some functionalities in survival analysis related to cancer datasets in the package NetSurvival.jl. I'm going to do like that. So we'll start by an introduction to the field that we are going to discuss, and after that we'll do a bit of a comparison with what existed before. Spoiler alert, it was a bit of C code packaged into an OR interface. And we'll discuss a real data example to see and to show how the code can be used, and then we'll reach kind of a conclusion. So yeah, it's still me. I don't know if you're on the page in terms of survival analysis, but to give you a brief recap, survival analysis is a piece of statistics. It's a statistical theory that deals with positive random variables that are censored. By censored, we mean that there is another random variable that hides the one that we want. In the graph on the right, you have a few patients. Each of them has a lifetime that is denoted T, and some of them died, and we know that they died, and so there is a little cross at the end of the line. And some of them we lost to follow up. They could also be patients. It could also be that the study just stopped, and so these guys are still alive, or we don't know. But we still know that they survived up to this point, and we don't want to throw out the information. Because the time that we want to model is the time to death, to the real death. So these patients need to be handled a bit differently that standard statistics does, and this is the founding of survival analysis. This is a field that relies heavily on counting processes and local martingales analysis to get stochastics and asymptotics and stuff like that. Here we have a context that is a bit different than the standard one, which is what is called a relative survival context. And so it will be clearer if I describe the random variables that we are dealing with. There is E, the excess lifetime. It's supposed to be the lifetime of the person with respect to the disease that we are studying, in particular some cancer. There is P, which is a population lifetime. It's supposed to be the lifetime of the person with respect to other causes of mortality. And so the patient can die from one or from the other that are supposed to be independent. The two risks are supposed to be independent, and I denoted O, the overall lifetime, which is just the minimum between the two. And then there is the standard censoring things. So you have C, a censoring time, that is another independent time. T, which is the minimum between O and C, is the time that we will observe. All the rest is not observed. And we will observe an information that tells us, as did the cross and the circles on the graph before, that the observation is censored or not. But the particularity in the field is that we do not know if the patients that we have actually died from the cancer or from something else. This is an information that is really hard to get from doctors and from cancer registries. Even if we want to model the risk with respect to the excess lifetime, we want to model the distribution of E and not the distribution of P. So everything else is just nuisance, and we want to get to the distribution of the random variable E. Since this cause of death indicatrix is not available in our datasets, standard survival analysis that I described right before is not applicable, and we need to do something smarter. So in terms of notations, we'll use S to denote the survival function of a random variable. We'll use lambda, the big lambda, to denote the hazard function of a random variable, which is just minus the log of S. And the small lambdas, or d lambda, to denote the instantaneous hazard, which is in terms of positive random variable on the positive part of the real line, which is our case here, quantities that characterize these distributions. Our goal, I just said it, is to estimate the distribution of E, let's say by its hazard. And for that, we have a few assumptions on the joint distribution of all these random variables. The few assumptions are that they are mostly independent from each other. The several causes of death are independent from each other. And there is one, the population mortality, that depends on a few covariates. And we use this covariate to describe the fact that an older man of age 82 doesn't have the same mortality risk as someone of age 42. even if they have exactly the same cancer, they don't have the same mortality with respect to the population part, and so the distribution of P varies from individuals to individuals, but not the distribution of E with respect to the cancer. In the computations, we will need to access the distribution of PIs, the population mortalities, which are extracted from standard life tables produced by the statistical offices in each countries. And in particular, it's instantaneous hazard, lambda PI, and all the code with respect to these rate tables was actually moved to another package because it's useful in other places of the infrastructure. And so it's moved to the ratetable.jl package. You go.
Given the relative survival context, we're going to introduce the standard estimators in the field. So when we're talking about the estimation of net survival, we are mainly talking about estimating the instantaneous or cumulative excess hazard. And for that, there are many methods that exist, but we're going to mainly be focusing on PowerPerme, which was introduced in 2012 and is mainly used in research. And when we're talking about net survival, people usually use this method. So it uses the inverse probability weighting. Here we're referring to the populational survival function. And the estimator is given by the formula on the slide. And the variance is estimated using the same weighting. And one good thing about this estimator is that it's biased but convergent and asymptotically unbiased. And what's really cool about Julia when coding this is that the code resembles the formula because we're using the same notations. And so when someone is going to read our function, they're going to understand exactly what it does as it resembles exactly the mathematical formula presented. One more cool thing is that in this function, 60% of the runtime is due to the exponential function, which is unavoidable, meaning that it's very thoroughly optimized. And now that we have our net survival functions, we want to be able to compare the net survival functions between groups. And so this is where we introduce the logrank test, the Crafeo logrank test, and where the null hypothesis aims to compare the excess hazards across partitions inside of a group. And to be able to do that, we first construct the z vector, which is the difference between the uncensored death process and its estimation under the null hypothesis. And from this, we're able to construct the test statistic under the chi-squared distribution under the null hypothesis, where the variance matrix is also given by the estimation in the slide. The null hypothesis is rejected when the p-value calculated is under a certain margin, an error margin, that is chosen by the researcher. Given the survival rates, it's also important to be able to separate it by cause. Here we did the crude mortality, which allows us to calculate the mortality rates separated by cause. So we have the mortality rate due to the certain disease studied and the mortality rate for the population. And the observed rate is going to be the addition of the two. So here it's with respect to the excess hazard, and this is with respect to the populational hazard. And to estimate this quantity, we're going to be using the Cronin-Feuer estimator, which estimates the observed survival function using Kaplan-Meier, and the excess hazard using one of the methods. Usually it's PowerPerme, but there are other methods that are there are two that are also included in the package, but we are not going to be presenting them. And lastly, an important functionality in the package is the NESI function, which allows us to estimate the sample size in yearly intervals, and it's given by the sum of the populational survival function. And the expected lifespan as well, so how many years left are on average for a certain group of people, which is given by the constants of the hazard rates in the mortality tables. This is implemented in the rate tables package that was constructed complementary to the net survival package because we saw a need to have an independent package that deals with rate tables as well. And it relies also on the expectation function from the distributions package.
we wanted to give you in a few screenshots a comparison with the O and C++ code. It's actually C code that was in the original version. If you look at the crude mortality estimator that we just introduced, you'll see that basically it's 3 lines of code, right? It's 1 comprod and 2 comsams. So it's not really complicated. But if you go to the OR package, yeah, here you have the nesty function, which is also very small. If you go to the OR code, then the number of lines goes crazy, and the code is mostly unreadable. It's not always commented in English. Comments are mostly wrong. Yeah, it was a pain. And at the end, yeah, the C code is even worse. And at the end, we were able to reach a size of code that is about 15 times as small, while having the same functionality and increase the readability. The code that we produced includes unit tests. It includes documentation that is readable in English with proper descriptions of what's happening in it, and we can actually trust the implementation that we made, while the original one is harder to trust. And on top of the cake, if I can speak like that, it's the time multiplier which goes a bit crazy, and so we have a runtimes that are about 20 to 30 times as fast, depending on the functions that you are using with respect to the original OR version, which is good if you consider that computing one survival curve used to take about 2 seconds. It goes down to about 0.1 seconds, 0.1 second. If you have 1 or 2 to compute, it's not a big deal if they take 2 seconds. But if you compute thousands in the middle of more complicated algorithms, then it can add up quite quickly. Most of the win in terms of time is due to carefully thinking the infrastructure and the classes, and in particular the rate tables, the tables in which hazard rates for the population mortality are given with respect to the age and the date and the countries of the patients. These tables were implemented in a horrible C code. And here basically this function just fetches a value in a matrix. And on this function we won crazy.
Having explained the functionalities of the package, we're going to present an example that shows you how you can use them and how you can interpret them. For this reason, we're going to be using the coloREC dataset, which is a rather small, basic dataset. It has around 6,000 patients that are diagnosed with colon or rectal cancer between 1994 and 2000. It has 7 variables. Age, year, and sex are going to be used to be able to get the populational hazard rates. And status for censorship, follow-up time, or survival time as well. Cancer stage, that takes the values 1, 2, 3, or 99 for unidentified. And cancer site, so colon or rectal cancer. And it's sourced from the Slovenian Cancer Registry. For this reason, we're going to be using the Slovenian population mortality rate. So we can extract the populational hazard rates. The first step in any data analysis study is to look at the distribution of our variables. So we're going to look at the age and the follow-up time. And as we can see that most of our patients are aged between 60 and 80 years old. And as for the follow-up time, it takes a quick dip rather quickly. And we can tell that at around the 5-year mark, we've lost a lot of patients. Given these information, we're going to apply the PowerPoint estimator, which uses this interface. It's also very similar to the R interface, so if anyone is used to the R interface, they can quickly adapt to the Julia one. And the one here can also be changed to any of the variables. That way we can get different tables. So let's say we include the variable sex. We can have a table for the male patients and another table with the female patients with the net survival estimator for these patients. And the table is given in daily intervals. It gives us back the confidence intervals, the variance, as well as the excess hazard and the survival and the excess estimated survival function. When putting the results in a graph, we get the first graph on the left, which is a little abnormal. But this is the same in R. It's not an issue from the code. It's just an issue with the data. We get large confidence intervals and also the probability, the survival probability that increases, which is not normal. But it's mainly due to the fact, actually we're going to explain that in a bit later. And when zooming in on the first 5 years, we get a more normal looking survival function that also quickly falls under 50% within the first 5 years. Let's look at the loss of accuracy, which is represented by the large confidence intervals. And for that, we're going to be looking at the NESI function that allows us to estimate the sample size throughout the study, as well as the estimated lifespan. So when looking at the expected sample size, we get that at the end of the study, we've lost almost 3,000 older patients. Here we defined the older patients as older than 65 and the younger patients as younger than 65. So we've lost more than 3,000 patients, older patients, and less than 1,000 for the younger patients. When you're losing this many patients, by the end of the study, you're getting a loss of accuracy because you don't have as much data as you should have to be able to estimate. And this is especially shown in the graph in the slide, where the slope for the older patients is much harsher than the one for the younger patients. And we can tell that at the beginning of the study, we had a lot of patients compared to at the end of the study. And as for the expected lifetime or the years left for each of these groups, we have on average 14 years more for the younger patients, which is logical. But also, it also means that at around 10 years, we've lost almost all of our older patients, a good majority at the very least. We can also cut at 10 years instead of 5, because we decided to cut at 5 when drawing this graph on the right. We can decide also to cut on the 10-year mark, but we decided on 5 because at the 10-year mark, we've already also lost a lot of patients. When running the crude mortality function, it's also interface-wise, it's very easy. You just apply the power per May estimator that we applied at the beginning. And at the 5-year mark, we can tell that out of the 64% of the patients that have died, 53% is due to the colon or rectal cancer, and 11% is due to other causes, which also helps justify the fact that we cut at 5 years, because we still have a lot of patients dying from the cancer and not from other causes. Lastly, we apply the Graphéo test to be able to compare the net survival functions between groups. And we found that only 2 variables are important in the study, which are the age, so younger and older patients, and the stage, because they both gave us p-values that are very, very small, and so they're necessarily very significant in the study. So in conclusion, the older and the more advanced the cancer stages, the lower the risk of survival, which is a very logical conclusion, which is why I said it's a very basic example, but it was mostly to show how you can use it and how you can interpret the results.
A small note before reaching the end. All this work is started only for the net survival case, but then we understood and we saw the infrastructure, and we are trying to build a bit more. And so there is this JuliaServe organization that was constructed to hold this work, but also infrastructure, and there are a lot of projects in it around survival modeling in more general terms in Julia. There will be more in the near future on this front.
So again, to summarize, survival analysis uses censored data, and the variable of interest is the time of survival. With specific cases, we have the cause of death that is unavailable or unreliable, which is why the relative survival field was born. To be able to handle such scenarios. Our Julia implementation is much faster, more concise, easier to read than ours, and making it future-proof. The JuliaServe organization has hopefully a very bright future ahead, and any and all contributions are more than welcome. Thank you.
Thank you very much.
Oh, and if there are any questions, go ahead.
Mike?
Any questions?
Hey, thank you so much for the excellent talk. I had a question on slide 18. You're showing the code where you could have the exponent syntax. Yes, the exponent syntax where you're saying you could, for example, change out age 65, have like different variables in the formula function there. I was curious, how well does the package right now handle intersectional populations? Say if I wanted to look at maybe age 65 as well as maybe by gender as well. Is the package right now capable of this intersectional analysis, or where is it at right now?
Yeah, we can actually, it groups people, so I don't, hopefully I understood the question right.
Yeah.
So if you want like age 65 and female, age 65 and male,
Yeah.
that can also be a possibility. You just add sex plus age,
Oh,
and
okay.
it would group them in that order.
Okay, thank you so much.
Any other questions?
Thanks. And actually, on the prior slide, I had another question. I was curious when it came to slide 17.
Okay.
Yeah. I was curious when you calculated follow-up time. How did you calculate follow-up time? Was that part of the NetSurvival package itself, or did you have to do that manually, or what was the process?
The follow-up time is it's data in the cohort. So when
Okay.
you're dealing with a data set that is used for net survival or survival analysis, usually it includes the censorship and the survival time. These are variables included in the data set. So it's not calculated, it's just the data
Just a given.
Yeah,
Okay. Okay.
The follow-up time is T in this slide. The follow-up time is just T on this slide. It's part of the data set.
Okay. Thank you.
Any other questions? If no questions, yeah.
Is there another kind of system or data set that you can use to sort of validate your findings with more sort of high throughput? Because obviously, like, cancer patients are very heterogeneous. The reason why they're in clinical studies is because they're dying anyway, and they're trying to. It's a last resort, right? So comparing patient to patient, it's you have to take into account what prior therapies they've had and all that kind of stuff. Is there maybe like another kind of data set that you can use in nature that's perhaps cleaner and easier to access?
No.
No.
The problem is that the datasets on cancer patients is rare, and to be able to pool cancer patients from several countries and several places, we are obligated to go through these methodologies. The cause of death is of course unattainable. There are other information in national databases, but when they are pooled in the global cancer registries, those are usually not available at all, and you get very few information about the patients themselves. You might get sometimes information about what they got treated with, and so you can use it as a covariate to check if the net survival of cancer patient that did had some treatment is better than others, to validate the treatment itself. That is one of the potential applications of this work.
Are there no equivalent model like databases for mice, for example?
For
Mice?
what?
I think what your question is basically asking if we can apply it to other than cancer data sets. Is that?
Yeah, or whether there's any advantage in finding other data sets that have like more data points and are more readily available than cancer.
Well, I think mainly survival analysis in the first place can be used for things that are even outside of life sciences. You can use it well, the most important thing here is that we're the main star, or like the interest when doing an analysis, whether it's relative survival or just survival, it's the time of death. So whether we're calculating it because of cancer or for other reasons, it can be done. It's just more of a researchers that are going to be using this tool that are going to be exploring other data sets more than us as statisticians.
The NetSurvival stuff is really for those kind of cancer registries where the number of line is also limited because the number of persons that do get colorectal cancer is not infinite. But there are on other survival issues, even in the medical context, data sets that are way larger, but not in the NetSurvival context. And there is this survivalmodels.jl that is upcoming that will probably do stuff to answer some of these questions, to build more strong models, right?
Thank you.
All right, so maybe if no other questions, I have one last question. So it's probably like it's more common when you see a statistical analysis is written in R, right? So when you transit from R to Julia, what are the challenges you encounter?
As someone who's going to be using the package, or as someone who
Developer.
developer. Well, the first 2 weeks when we were starting this project, we were looking at the R code, and it was really horrible to look at. It was really hard to read. And so we mainly decided to give up on looking at the original source code, and we just looked at the math part and decided to apply the math logic besides instead of the R logic, because the R had not a lot of logic in our opinion.
Okay, great, thanks. Yeah.
You're welcome.